my wonderful chemistry students. Okay, this is what we're going to be accomplishing today. We're going to spend the first part of class practicing some accumulative knowledge items, so prior chemistry that we've already covered. And then the last 20 minutes of class, you're going to be taking the accumulative knowledge quiz. And then when we get back together in the following class period, we will grade that. Okay, so everyone, what we're going to be looking at, make sure that you keep an eye on the clock because you do need 20 minutes. So you want to be starting the quiz 20 minutes before class ends so that you can turn it in at the end and then we can grade it next time. Okay, first prior knowledge thing is trends. So reminder, there's three main trends that we have focused on: atomic radius, ionization energy, and electronegativity. We've been talking about electronegativity the most lately. Do you remember how we've been recognizing and seeing that fluorine has that greatest electronegativity? It's our bully of the periodic table. It has the greatest affinity or attraction for electrons, where the noble gases, they have a full energy level, so they aren't trying to gain those electrons, but they are trying to hold on to those electrons, and that's ionization energy. How much energy would I have to add before I can pull that away? So ionization energy is the largest in this corner of the periodic table. The relationship between atomic radius and ionization energy, or atomic radius and electronegativity, is inversely proportional. When these are large, then atomic radius is small, or atomic radius is our largest over here, directly opposite from those. Okay? When we move across a period, because look, here's our arrowhead, right? When we move across our period, atomic radius, we're moving away from that big atomic radius. So we are decreasing in atomic radius. But we are increasing in ionization energy, right? We're getting closer to where it's the largest. And then as far as electronegativity goes, as we move across a period on the periodic table, we are also increasing. That's because the relationship between ionization and electronegativity is directly proportional. When one gets big, the other one gets big. But the relationship between ionization energy and atomic radius is inversely proportional. When one gets big, the other one gets small. Or if one's getting small, the other one's getting big. Same with electronegativity and atomic radius. They are inversely proportional. So when we are decreasing in our atomic radius, we are increasing in our electronegativity. Okay, so similar concept here, but now we're considering our arrows are telling us down a group. So if I'm going down a group, I'm getting closer to my large atomic radius, so I'd be increasing in atomic radius. And then if I'm moving down a group, I'm moving away from electronegativity being big, and I'm moving away from ionization being big, so we'd be decreasing. And the relationships that we talked about down here, we're seeing that there. That ionization energy and electronegativity are directly proportional. When one gets small, the other one gets small. And the relationship between atomic radius and ionization energy is inversely proportional. When one is big, the other one is small. Or between atomic radius and electronegativity is inversely proportional. When one is getting big, the other one's getting small. So let's think through this in terms of electrostatic force. So everyone, I apologize. I wrote in terms of electronegativity. I meant to say in terms of electrostatic force. So will you please change that on number 2 and number 3? So a reminder, electrostatic force is the force of attraction between charged particles or repulsion between charged particles. So the particles that we're going to talk about right now are the nucleus of the atom and the electron. So we have atom A, which is a larger atomic radius, and then we have atom B, which is a smaller atomic radius. So we have a nucleus, and then there's electrons. And so we think of like an electron out here, and then we have our nucleus and electron. which atom has greater electronegativity, and then we got to justify this in terms of electrostatic force. So electrostatic force is the force of attraction that occurs between charged particles, and that's specifically electronegativity when we're referring to the nucleus and electrons, meaning that the greater the electrostatic force, the larger the electronegativity. If we have a small radius, that means that the nucleus had a strong attraction to its own electrons, and so it has a much higher likelihood it has a large electronegativity. Okay? So the greater I'm trying to think of the wording. The greater the electrostatic force, now we're going to be saying this a little bit, so I'm going to change. We're going to have electrostatic force, okay? So the greater the electrostatic force between our nucleus and electrons, the greater the electronegativity, and the smaller the atomic radius. Or we could change this one a little bit. So the greater the electrostatic force between the nucleus and electrons, the greater the electronegativity. And we could say, like, which results in a smaller atomic radius. So then the question is, which atom has greater electronegativity? Well, according to this, so thus, atom B would have greater electronegativity. So the greater the electrostatic force between the nucleus and electrons, the greater the electronegativity, which results in a smaller atomic radius. Thus, the atom B would have greater electronegativity. Similar concept here. We have atom A, again, is larger than atom B, which has greater ionization energy. And we're going to put this in terms of electrostatic force. So ionization energy is how strongly they're holding on to those electrons, meaning how much energy do I have to add before I can remove that electron, or before I can remove this electron. Okay? So the stronger the electrostatic attraction a nucleus has for its electrons, the greater the ionization energy, or the more energy we would have to add. Okay, so let's add that in there. So the greater the electrostatic force between the nucleus and electrons, the greater the ionization energy will be. Okay. And so again, we're going to say, which results in a smaller atomic radius. Okay. And so now that we've recognized that this small atomic radius means a greater attraction, and which would suggest that we have a higher ionization energy, then atom B would have greater ionization energy. So thus, atom B would have higher ionization energy. So one more time, that relationship between atomic radius and ionization energy is inversely proportional. When one is big, the other one's small, or when one is big, the other one's small, when one is small, the other one's big. Same with atomic radius and electronegativity, inversely proportional. When atomic radius is small, then electronegativity is big. But the relationship between ionization energy and electronegativity is proportional. When one is big, the other one is big. Now we're talking about if bonds are polar or nonpolar. So remember how if we do the difference in electronegativity, that if that number falls between 0 to 0.4, that would be a nonpolar covalent bond. But if it falls between 0.4 and 1.7, that would be a polar covalent bond. So we're going to use our electronegativity table. Everyone on the quiz, I've recorded these scores for you, so they are already on the quiz. You don't need the separate table. So if we have boron and chlorine, so I'm going to find boron and I'm going to find chlorine. So chlorine has an electronegativity of 3.16 and boron is 2.04. So the change in, or the difference, means I'm going to subtract them, and I'm always just going to take the bigger one minus the smaller one. So when I run that, I get 1.12, and it's falling in that polar covalent range. So if it's polar, we need to draw a dipole arrow and correctly indicate the polarity of the bond with the partial positive and partial negative. So dipole arrows always point at the greater electronegativity. Since chlorine had greater electronegativity than the boron, that's why my arrow points at it. And since it has greater electronegativity, that means it's pulling on the electrons more strongly. So the electrons will spend more time there, and our negative electrons give this a partial negative side. The partial negative will always go with the head of the arrow. The partial positive will always go with the tail of the arrow. Now looking at carbon and hydrogen, carbon has 2.55 and hydrogen has 2.20, so this would be 0.35. So it falls in the nonpolar covalent range. So we do not put a dipole arrow only for, and we do not put partial charges. That would only be for a polar covalent. So this is nonpolar covalent. Okay, so this is what I want you guys to do. The electronegativity of nitrogen is 3.04 and carbon is 2.55. Fluorine is 3.98 and iodine is 2.66. So determine if they are polar or nonpolar. If they are polar, I want to see dipole arrows and partial charges, and then if it's nonpolar, we'll just put nonpolar covalent above it. And so take a moment, do that, and then we'll start the second videos, and I'll have that completed, and so you can check your work.